Right, this is going to be part two of our network problems. And again, for this part of the lesson, we're going to be talking about a maximum flow problem. This is going to be, again, look similar to the other two problems in part one, but it's going to be very, very different. Um, and again, in part one, we looked at the minimum spanning tree, which every location had to be interconnected. In part two, we looked for the shortest path, the shortest route problem from a starting point to a finishing point. How do we most quickly get through the network? And this is a maximum flow problem. This is a problem that's going to be civil engineers in terms of flow through a system of pipes or automobiles through a network of streets and roads, any type of commodity that's flowing through from one point to another. And I'm going to use the context of today of water system as we look through and how much water can flow through a series of pipes and pump stations. So here's how this problem works. Again, it's going to look very similar. Now you'll notice, first of all, the network looks very, very similar. There's an origin, and then there's a destination. And we're going to hypothetically say for today that our origin is our origin is going to be a reservoir. Of water, and our destination is going to be a city that needs the water. And so all of the five locations between the reservoir and the city are pump stations, and the paths that are shown are pipeways. So this is a pipe from O to A, and this is a pipe from O to B, from O to C, and so forth. The other thing that's going to be extremely different and unfortunately sometimes confusing for students is that the numbers that are associated with each one of these, each one of our pathways is a flow capacity. And so it's the capacity. This is, again, these are, I don't know how my drawing will be, but these are pipes. And so from O to A, that pipe has a capacity of 5. And you can think of that as 5,000 gallons per hour or whatever you'd like to think of. But it's something that's, in this case, water that's going in and then water that's coming out. But it can only has a capacity of 5. And so these then also, and we'll talk about later, become constraints. The last thing I want to talk about is the objective that we have is different. The objective is to determine what is the maximum flow from the origin to the terminal using any combination of paths. So we want to push, if you will, as much water through this network using any of these possible paths to get as much water, max, as much water as possible from our origin, from our reservoir to our terminal. Okay, so hopefully that sets the stage for what we're going to do. The other thing I want to say is that I've already modified our network a little bit from previous, but you'll notice in some cases we don't, in only a few cases do we have two-way water system. So for example, we have a pump house at A that can push water out to B and D, and then B can push water back to A. All right. So that's the and everywhere else is this water can only go from B to C. it can't come back from C to B. So in this case, let me hopefully you've already anticipated how many decision variables are we going to have. Well, let's look. Let's count them up. There's 3, 4, 5, and there's 3 more. That's 8, and then there's 9, 10, 11, 12, 13, and if I've counted correctly, 14. Counted them all, 14. 14 decision variables for our problem. See if I've counted those correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I believe so. So we're using, again, any combination of paths. So now let's begin our formulation. Well, let me say one more thing before we do that. Again, this has the same general structure as our previous problems, but it's going to have one twist, and we'll talk about that in just a minute. And it has to do with the objective function. All right, so let's look at this. And this is how we're going to solve this, because the biggest problem with our maximum flow is let me contrast this to our shortest route. For our shortest route problem, we knew that we had one person walking through one supply and one demand. Well, the problem we have now is we don't know from the outset how much water can pass through our network from origin to the destination. We have no idea how much can pass through. And so what we're going to do is to remedy that. It's a modeling trick. Is the following: we know if we have, well, let's just say hypothetically, if we have, I'm going to pick a large number. Let's suppose we have 300 units. If we have 300 units, 300 gallons that arrive at the destination, then how many do we have to have at the origin? Well, that means if 300 arrive here, we have to have 300 to start. But our problem is we don't know what this starting number is. How do we do that? And so what happens is for the liquid, the water here that passes through the network, it has to equal to what is at the origin. And so what we say is a construct is whatever comes out of the destination is what whatever comes out of the destination is what has to start at the origin. And so this in and of itself is a balance mechanism that keeps this network in balance and pushes through as much as we possibly can without overfilling or breaking the network. Okay. So that we'll talk about this more here in the next slide. So let's look at our decision variables. And again, I'm going to start with an example. We're going to say OA is going to be the amount of water flowing from O to A. That's going to be the definition for our decision variable that corresponds to this path or to this pipe. All right. And so again, in general, we're going to say IJ is the amount of water flowing from I to J. And in this case, again, I and J can really be any one of these. I can be O, A, B, C, D, E, T. And similarly, in this case, J can be O, A, B, C, D, E, T. So it can be any of these. Notice too, we have this new path T to O, which is the amount of water flowing from T to O. Right? So this is the definition of our decision variables. All right, now let's look at the objective function. And this is the one that's going to be a little bit tricky, because in this case, it is hopefully you're, again, by its name, it's the maximum flow problem. So you know it's going to be the maximum, maximize flow in through, let me say through the network. And now this is going to blow your mind. We're going to say max flow, maximize our objective function, which is the flow. But that's going to be, Z is going to be equal to T0. So we have one term, which is, and you'll remember T0, B to O is the amount of water flowing from T to O. So our objective function now is just this one term, T sub 0, which is the water that passes along this arc. So whatever comes out here has to go back into here. And as long as this T sub O, if that's as large as possible, then we know that we can flow the max as much as possible through that network, because whatever comes out of here has to start from, whatever comes out of T has to have gone in at O. And so this is again, this balances the whole network. One of the things that I want to say too here, and this is, I'm just going to say this briefly, and hopefully some of you will understand, but if we look at our network, we can see, and I'm going to erase this, if we look at our network, and these are our capacities, if we look there, we know we can already say that the most that we can get through this network is 15,000 gallons or whatever it is because the most that can come into T on any one of these paths is 15. We know that the most that we can ship out of the origin is 5 plus 6 plus 5, or 16. And so by definition, every time we look at this in this way, this is a cut. So in other words, if I took a bulldozer and cut through cut these two pipes, then I've completely separated the origin from the destination, and I know that no more than 15 units can flow across that cut. Well, there's a theorem in linear programming and for these types of problems, it says the maximum flow equals the minimum cut. And it's just as hard to find the cut in a network as it is to find the maximum flow. So it doesn't help. But what it does help is, and I'm not going to show this, but it does help to determine, much like in our critical path, being able to identify the minimum cut allows us to know which pipes must be improved. Hypothetically, let me just say this again. If it happened to be that 15 was our maximum flow, and this was, and our cut was here, then in order to get more than 15 to our destination, one of these two pipes, either D to T or E to T, would have to be improved, or both. Hopefully that makes sense. So I'm just going to leave that. If that makes sense to you, good. If it's not, if it doesn't, don't worry about it at this point, but you may run across that again if you at some point. Okay, so now that's the objective function. Let's talk next about the constraints. This is an unusual problem because it does have the same structure, and if you'll notice now, we have no origin, we have no supply, and we have no demand constraints. We will have 7 constraints, as we have previously, 7 constraints that correspond to each one of these locations. But if you'll notice, every one of these 7 constraints is now a transshipment constraint. So in every case, O, whatever goes into O has to come out of O. Whatever goes into O has to come out. Whatever goes into A has to come out, and so forth. So all of these are transshipment nodes, and whatever goes in has to equal to what goes out for all 7 of these nodes. So as before, I'm going to do a couple of these and then I'll leave them to you. And in this case, the first one that I'm going to talk about, let's just look at D, and then let's look at the origin. So I'll start with the origin. So for the origin, what's going in? Well, TO is the only thing that's going in, and what's going out is OA plus OB plus OC. And for D, what's going into D, you'll notice there's 3 pipes going in and 2 pipes coming out. So what's going in? A to D is going in, B to D is going in, and E to D is going in. Oops. And what's going out? D to E and D to T. And again, we've done these so many times, I'm going to leave the others A, B, C, E, and T, although I will talk to T since it's a little bit. What's going into T? D to T plus E to T, which we've already talked about, and then that's what leaves. D is from T to O. I'll leave the others then for you to work through. Now there's another set of constraints that we haven't talked about with this problem. And those constraints we haven't, if you'll think about it, if you've been paying close attention, we haven't yet used these numbers. We didn't use them in our objective function, all right? And so there's a whole different set. I'm going to erase everything. There's a whole different set of constraints that are capacity constraints. And what that is that every one of our pipes, if you will, has a capacity, has a limit, with the exception of T to O. And so what we're going to have to account for is O to A is going to be less than or equal to 5 units. And we're going to have to say O to B is less than or equal to 6 units. And we're going to have to say O to C is less than or equal to 5 units, and so forth, all the way out until we for all 14 of those constraints, D to T is less than or equal to 8 units, and of course E to T is less than or equal to 7 units. And so all of those have to be will have to be accounted for. But again, the only path, the only pipe that doesn't have a limit is T to O. Okay, because we're going to maximize that that value, make that as large as possible without limit. Okay, and so with that said, again, you should be able to now infer and get, this is the entire formulation for this maximum flow problem. I to J is the amount of flow from location I to J. We're going to maximize the flow from T to 0. All right. We're going to have 7 balance constraints for origin, A, B, C, D, E, and the terminal. And we're going to have 14 capacity constraints. If you count these up, each one of these pipes, if you will, have a capacity. And of course, as always, we don't want to forget our non-negativity constraints. All right. So that's our complete formulation. And now, as before, this is the solver window for the max flow problem. Again, you'll be able to pull this up on Excel, but this is that. And again, don't forget, this is a maximization problem. We've got 2 sets of constraints. These are the transshipment constraints, so you can recognize that because they're equal. And then these are going to be the capacity constraints, and you can recognize that because it's less than or equal to. Make everything non-negative, select simplex, select solve, and we're going to come up with a solution that we'll see in the next video. Again, if you have any questions, I am happy to help.